In this video, we take a look at our final set of indeterminate forms. So, on one hand, you should be happy, right? Because we're finally getting to the point now where we would have looked at all these various indeterminate forms and different ways that we can evaluate them. But on the other hand, these are, I would say, are the trickiest types, right? These are the least intuitive results as far as indeterminate forms and limits are concerned. However, there is a pretty set process by which we're going to evaluate them. And the good news is this is a process that we've seen before. Again, it might not be the most intuitive from an algebraic standpoint, but it will always work and it will always produce the desired result, right? So what are these forms? Well, they're basically three forms. They're different, but they have one common thread to it. So here are the forms. They're forms that look like 1 to the infinity, or 0 to the 0, or infinity to the 0th power, right? So these are all a little bit different in the sense that, notice they all have different bases, right? And two of them have different exponents. But what they have in common is basically this. Instead of a product or a difference of functions, what you have now is a function raised to another function as far as a power is concerned. And so, for instance, this particular one here is saying that the base is approaching 1, but the exponent is approaching infinity, right? Getting very, very large. This is saying the base and the exponent, they're approaching 0. So both the base and the exponent is getting arbitrarily small. This is saying the base is getting arbitrarily large, but the exponent is getting arbitrarily small, right? How do we handle all of these? Well, what we do is we're going to use the familiar change of base. So change of base approach, where instead of having a function raised to a function, I want to have a constant base. And then what we're going to do is, so let me again just kind of give you the general procedure here, is we're going to take e and then raise it to the power ln of f of x to the g of x. So it's like we take, my parentheses there are unbalanced. So we have there and then there. So it's like we first take the ln, and why do we take the ln? Because it gives us the opportunity to bring down the g, right? To get it out of the exponent, right? But then to balance it, I can't just do the ln, I'm going to do e raised to that particular power, right? So I can change from this functional base, this base that has a variable, to this base that's now a constant. And then I can bring down the g and put it in front, right? So what I'm going to end up with is this. E to the g of x times the ln of f of x, right? And that is the general procedure. Now, so now think about it. In each of these three cases, we're going to bring the exponent down. So it's gonna change from essentially something that has an exponential form to something that has a product form, right? And then we're going to have to apply algebra to this product in order to get it to a situation where we can use L'Hopital's rule. So there are a few key steps here, and we'll carefully go through these examples so you can see how they all play out, right? So let's go through a few examples highlighting the particular process. Now, this is one way to do it. If you remember, when we had these expressions earlier and we were just worried about taking the derivative, we could either use the change of base or we could end up using ln and using implicit differentiation. I'm going to forego using the ln. I'm going to end up using this form or this process in all the examples just to keep it consistent, right? Because there'll be enough stuff going on that I don't want to focus on, okay, well, let's do it this way, or then let's change a particular method, right? Let's keep the method consistent and look at how the examples play out in each of these forms. So let's start with something like the limit as x approaches 0 of 1 plus 4x all to the 3 over x. All right? So let's see what happens. So here's the base. So the base here, if I take the limit as x approaches 0 of 1 plus 4x, well, that approaches 1. The limit of the 3 over x, so the limit as x approaches 0 of 3 over x, well, that's that infinite limit form, right? You have 3 over 0, so that's our infinity, right? And in this case, so what do we have here? Yeah, we have something of 1 to the infinity form. And it's so tempting to say 1 to anything is equal to 1, but that's only if that anything is a number. Infinity is not a number. And the base is not actually equal to 1, it's just approaching 1. X is getting very, very small, so that means that this is getting very, very close to 1, but it never actually is equal to 1. Right? Okay, so let's apply our change of base formula and see what happens. So we'll have the limit as x approaches 0, so I'm going to take e and then the ln of this expression, the 1 plus 4x to the power 3 over x. And then use that property of the natural log that allows me to bring the 3 over x and put it in front, right, the ln as a multiplier as opposed to an exponent. So this is the limit as x approaches 0 of e to the 3 over x times the ln of 1 plus 4x. All right? Okay, so what do we do in a situation like this? Well, one of our limit properties, again, since the base is now a constant, I can focus on the limit of the exponents. So I can say e to the limit as x approaches 0 of 3 over x times the ln of 1 plus 4x. Now what happens is now if I look at this product, right, so I've changed it from this kind of exponential form to now a product form, and this factor, the 3 over x, approaches infinity as x gets very, very small. And then as x gets very, very small, the other function now, the ln of 1 plus 4x, that approaches 0, right? Because the inner part approaches 1. The natural log of 1 is 0. So it approaches 0, right? So we've actually converted this 1 to the infinity form to now an infinity times 0 form. Now we're almost there, because what we would like to do is to get this in either 0 over 0 or infinity over infinity so that we can use L'Hopital's. But in this case, the algebra is very, very straightforward. There's no massive trick, because all I have to do is to treat these now so as two fractions, just multiply the top. So I'll have 3 ln of 1 plus 4x. And then multiply the bottoms, just have an x there. So now when I say, well, what form do I have? Well, clearly the top approaches 0 and the bottom approaches 0. So it's 0 over 0. So now I can finally apply L'Hopital's rule to this limit. And the thing is, I can't forget to keep the e, which is in part why I tend to focus on using this particular method because many times you can try to use the other form where you just use the ln, but you almost always, students almost always forget to do the e at the end. If I keep the e, it's a constant reminder that my final answer is going to have e to some power, right? Okay, well, let's figure out what that power is. So L'Hopital says take the derivative of the top. When I differentiate 3 times the ln of 1 plus 4x, what do we get? Well, we have a 3. Then the derivative of the ln is our reciprocal, so 1 over 1 plus 4x. But then I have to multiply by the derivative of 1 plus 4x. That's because of my chain rule. So I'll have an extra 4 there. And then the derivative of the bottom is 1. All right? Well, before we evaluate this, just for good measure, let's simplify this. Well, we have this product here in the numerator. So it ends up being 12 over 1 plus 4x, right? So that's what this entire limit reduces to. And now this is no longer indeterminate. The numerator is a constant value of 12. The denominator approaches a value of 1 as x approaches 0. So what do we end up with? Here's our answer. It's e to the 12 over 1, or this is e to the 12th power. Right? And what I will say is the majority of questions, right, the majority of limits of these 3 forms, the 1 to the infinity, 0 to the 0, or infinity to the 0, 99.9% of them end up with e in the answer. You're wondering, where does the e come from? It's because of that change of base formula. All right, so there's one. Let's take a look at another one. Let's try, so this would be, what, example 2? So let's try something that on the surface looks a little simpler. Let's take the limit as x approaches 0 plus of, x to the 2x, right? So what form is this? Well, as x approaches 0 plus the base, which is x, that approaches 0, right? And then the exponent, which is 2x, as x approaches 0 plus, the 2x approaches 0, right? So yeah, this is of the form 0 to the 0, and we're told so many times that 0 raised to any number is 0, but the thing is that that particular rule, 0 raised to any number is 1, or actually, I combined those two incorrectly. 0 raised to any power other than 0 is equal to 0, and then any number other than 0 raised to the 0th power is 1. So how do we combine it like this? Like if you have your calculator handy and you type 0 to the 0th power, you're quite likely going to get an error, right? It's not something that is defined in basic scientific calculators. Now, more advanced computer algebra systems, they know what this is, right? But let's see if we can figure out what it is. All right. Well, we're going to use our change of base formula, so I'm going to replace x to the 2x with e to the ln of x to the 2x, right? And then right away I can bring down the 2x, so I'll have the limit as x approaches 0 plus of e to the 2x times the ln of x, right? And again, the base is now a constant, so I can figure out what happens to the exponent. So let's write that down and see what happens. So we have e to the limit as x approaches 0 plus of 2x times ln of x. Now, as x approaches 0, 2x approaches 0. But as x approaches 0, remember the natural log has an infinite limit at x equals 0. It goes off to negative infinity, right? So there we have this product again of something that's getting very, very small and something that's getting arbitrarily large in a negative way. Well, what's going to happen to the product? What's going to cancel what out? Well, let's see. Well, in order to evaluate this using L'Hopital's rule, right, I have to somehow get this as 0 over 0 or infinity over infinity. Now, one common trick that happens a lot in questions like this is when you have a product of A times B or B times A, you can write this as B divided by 1 over A. So multiplying by A is the same as dividing by 1 over A. So I can do this strange thing that seems like counterintuitive, like we normally don't do this, right? But I can write B times A as B over 1 over A, right? And if I do that, I will actually get it in the form that I need. That's a strange thing about some of these products, is that I can get it in the form that's required to apply L'Hopital's rule by doing almost, I don't really want to say a backwards algebraic step, but it is counterintuitive to what we normally do. But who's to say what's normal, right? It's just that just because it's something that we've done, forever, that doesn't make it normal. It makes it familiar, right? But we just have to become familiar with the unfamiliar. So what do we do here? So I'm gonna write this as, I'm gonna keep it as 2 ln x, right? The natural log of x, and then I'm gonna divide by 1 over x, right? So I'm gonna divide by 1 over x. So I'm writing the product of, so I'm keeping the 2 ln x in the numerator, and then I'm taking this factor of x and dividing by its reciprocal, right? Because now this is really what I want. Because as x approaches 0, we know the natural log that approaches negative infinity. And then as x approaches 0, 1 over x approaches infinity. And that's what we need in order to apply L'Hopital's rule. So this is where I'm going to put my L for L'Hopital. So I have to differentiate the top and differentiate the bottom. So let's see what happens. I have e to the limit as x approaches 0 plus. When I take the derivative of 2 ln of x, I get 2 over x. When I take the derivative of 1 over x, I am going to get negative 1 over x squared. Right? Well, how does this simplify? If I have 2 over x divided by negative 1 over x squared, so that's 2 over x times negative x squared over 1. So this comes out to be negative 2x. So that's what this simplifies to. So I have e to the limit as x approaches 0 plus. So this fraction reduces to negative 2x. So now I can evaluate it as x approaches 0 plus. So this ends up being e to the negative 2 times 0, which is 0. And e to the 0 is 1. Right? And that's what this comes out to be. Right? So the limit of this x to the 2x, let's go all the way back to where we started. So the limit of x to the 2x as x approaches 0 plus, that limit is 1, right? All right, let's try another example here and see what we have. So let's try, so this will be a third example. Now let's say we have the limit as x approaches pi over 2 minus, And what do we have? We have the tangent of theta raised to the cosine of theta, right? Now let's see what oh yeah, why do I write? Well, actually, yeah, let me put theta here just for a little bit of variety. I think that's what I intended to do, right? Okay, so let's see what happens to the tangent of theta as theta approaches pi over 2 minus. So the limit as theta approaches pi over 2 minus of tangent of theta. Well, again, going back to properties of tangent, we know that the tangent has infinite discontinuities or vertical asymptotes at every odd integer multiple of pi over 2. So that means pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, and also negative pi over 2, negative 3 pi over 2, negative 5 pi over 2, etc. So as theta approaches pi over 2 from the left, the tangent function goes off to positive infinity. And then what happens to the exponent? Well, as theta approaches pi over 2 minus, the cosine function, well, that approaches 0. So this is of the form theta to the 0. Not theta, infinity to the 0, right? And what does this mean? Again, this is really strange because this is saying you have a function that is getting arbitrarily large raised to a function that is getting arbitrarily small. How does it work out? How does it reconcile? Is it, you have a big number raised to a small number? How small is the small compared to the magnitude of the large? We don't really know, right? So again, it's one of those things that we can't tell by looking. Okay, well, let's do our change of base formula. So I am going to write this as e to the ln of tangent theta to the cosine of theta, right? And then bring that cosine down, right? So we'll have the limit as theta approaches pi over 2 minus. Bring down so we'll have e to the cosine of theta times the natural log of the tangent of theta. And what happens here is so now what happens is we have the 0, right? We have 0 times infinity because the tangent goes off to infinity. And as the tangent goes off to infinity, the natural log will go off to infinity as well. So this form is now converted into this form, 0 times infinity. And the question is, how does this work out? Well, we're going to do that same, again, strange trick for taking this product, and instead of multiplying by cosine, I am going to divide by secant, right? In other words, I'm going to divide by the reciprocal of cosine. Well, the reciprocal of cosine is secant. So algebraically, these things are equivalent. So I'll have the e to the, then I'll have the natural log of the tangent of theta. So natural log of the tangent of theta over the secant of theta. And then what I'll do is, let me go ahead and now have the limit in front of this. Again, because the e is a constant that never changes, and by continuity, actually what we're doing there is using the fact that the exponential function is always continuous. So we have the limit as theta approaches pi over 2 minus, and then I have my ln of the tangent of theta over the secant of theta. All right, so this is now the form that we needed. It's infinity over infinity. Right? So now we can take the derivative. Well, let's see what happens. In fact, let's go ahead and do the derivatives off to the side here because they might get a little messy, but we'll see. So if we take the derivative with respect to theta of the natural log, come on. So the natural log of the tangent of theta, that's going to give me 1 over tangent, and the derivative of tangent is secant squared theta, right? So I'm going to end up with secant squared. Now secant squared is 1 over cosine squared, and tangent is sine theta over cosine theta. How does that simplify? Well, we'll have so we'll end up having, okay, let me write it like this: 1 over cosine squared theta times the reciprocal here, cosine theta over sine theta. So we end up getting 1 over cosine theta sine theta. So that's what we end up getting, right? Cosine sine. Now, there's a nice way to kind of handle this. And again, using a double angle identity. Now, if I had a 2 here, so if I multiply the top and the bottom by 2, right? I could have, so if I put a 2 here, let me do it like this. So 2 over 2 cosine theta sine theta. That will give us 2 over sine of 2 theta. So I could use a double angle identity here. So depending on how the bottom works out, we'll see which of these forms is going to be most convenient. But that's the derivative of the top. The derivative of the bottom, well, that's a little bit more straightforward. That's just our basic secant derivative. So that's secant theta tangent theta, right? Okay, so let's see. So what we have to do is we have to take this, any one of these. Let's say we take this one and then divide it by this, right? So if I take 1 over cosine theta sine theta. Actually, we could do this. So sine theta, and then divided by this, so times 1 over this reciprocal. Let's see how that simplifies. Well, 1 over cosine I know is, well, there's several ways we can do this. So I'm going to write this as 1 over cosine theta sine theta. Now 1 over secant is cosine, and then 1 over tangent will be cosine over sine. So we have this gone, this gone. So it looks like we're left with cosine theta over sine squared theta, right? So that's going to be when I apply L'Hopital's, we'll have e to the limit as theta approaches pi over 2 minus. When I take the derivative of the top, I'm going to get this form, which I rewrote it in several different ways here, right? And then I ended up using this particular form, and then the derivative of the bottom is secant theta tangent theta. So then having this on top, now dividing by secant theta tangent theta is the same as multiplying by its reciprocal. So that's why I took the reciprocal here and multiplied. And then I kind of rewrote this reciprocal and realized that, hey, these cosine factors will cancel out. So I left with a cosine in the numerator and a sine in the denominator. Put my parentheses there. All right, so this is what we have left. Cosine of theta over sine squared theta. And now let's try to evaluate it. So if I try to evaluate the top, the cosine of pi over 2, well, that's 0. And the sine of pi over 2, well, that's 1. So it's no longer indeterminate. So what I'm left with now is e to the 0 over 1. So that's e to the 0, which is equal to 1, right? So that's what our limit ends up being, right? And let's just see what our original problem was. Right, it was the limit as theta approaches pi over 2 from the left of tangent theta raised to the cosine theta. So again, lots of trig, lots of derivatives, lots of algebra for sure, but we end up being able to evaluate this indeterminate form, coming up with an answer of 1, right? So there are some examples of other indeterminate forms. They're trickier because they're even less intuitive than our other indeterminate forms, the 0 over 0 or the infinity over infinity. And again, it involves using this important concept of changing from one base to another base. And our goal is always to convert these forms into base E, because that's the easiest base in which to do calculus, right? So hopefully you'll find these examples useful, and it gives you some opportunity to practice these less than intuitive limit problems. I'll see you in the next video.